Liquid chromatography is a technique used to separate mixtures of chemical compounds or biomolecules in solution, based on difference in the compound's relative affinities for a liquid mobile phase and a solid or liquid stationary phase held within a column. The type of liquid chromatography is directly dependent on the type of interaction that is going to be exploited to achieve a successful separation of components. Some examples are chromatography based on polarity, molecular weight, charge, specific interactions, and hydrophobicity. Ultra-high pressure liquid chromatography, UHPLC, is a powerful and robust analytical technique. This technique has the same principle as the HPLC, which is conformed by 4 components that are involved in the process. The components are pump, injector, column and column heater, detector, and data system. UHPLC has the advantage of increased separation efficiency, improved resolution, shorter analysis times, and at lower operating cost compared to HPLC. This is due to a low particle size diameters of 2 micrometers in a short column that result in a higher internal pressure with the corresponding optimal linear velocities. Our equipment is a modern LC system that has compatibility with UHPLC and HPLC protocols, providing this way reliability, robustness, and repeatability to the experimental procedures performed. The main components of this equipment are as follows. First is the mobile phase. Here, the solvent runs continuously through the system and pushes the sample throughout the column. The solvent is stored in a tank located at a higher elevation than the pump, as to maintain a slight positive head pressure on the pump inlet. Then, a solvent filter is inserted to purge any residue that could alter the system and the sample. The mobile phase is pumped to the lower part of the equipment. Here, the solvents are mixed automatically according to a proportion established in the data system. This equipment possesses a quaternary pump, which means it can mix 4 different solvents in the mobile phase. We can see that there are 2 paths to pump the mixture. The red one corresponds to the HPLC option, and the blue one goes to the UHPLC system. Also, in this section, the tubes of the system eliminate components that could cause damage to the equipment or cause interference on the readings. The components of interest go to an autosampler, which is the second main component. The autosampler stores the sample vials in a temperature-controlled environment and injects a specific sample automatically. Using the data system, the autosampler decides which sample is going to be introduced. Therefore, multiple samples can be performed in one run. This equipment in particular can store 96 samples in 2 plates, each plate carrying 48 samples. The third component is the column. This is packed with a stationary phase that separates the chemical components of the sample based on different chemical or physical properties of the compounds such as polarity, size, and charge. In this case, we have reverse phase silica-based column. Here is where the main difference between HPLC and UHPLC occurs. The column can be packaged with the same material, but in UHPLC we can use a particle size of less than 2 micrometers, resulting in a higher pressure. This allows optimal linear velocities due to smaller particle size in the column. Also, the narrower the column, the greater the mass sensitivity. The fourth component is the detector. This element receives the output of the sample separation and monitors a physical or chemical property of the components while they are eluted from the column. In this equipment we have 2 detectors, fluorescence detector FLR and photodiode array PDA. Fluorescence detectors are very specific and selective among the other optical detectors. This is normally used as an advantage in the measurement of a specific fluorescent species in a sample. On the other hand, PDA is used for obtaining spectral profiles of molecules. Finally, a chromatography data system translates the signal from the detector into a chromatographic spectrum. This allows the control of the system for specific conditions that could be defined by a protocol, like a set of temperature on the column oven, or the proportion of the mobile phase and the order of sample injections. The research group led by Dr. Daniel Jacobo conducts studies to identify, produce, and extract compounds of nutraceutical value for different sources. One of these studies is based on increasing the concentration of phenolic compounds in carrots to take advantage of their antioxidant, antiviral, cardioprotective, anti-obesity, anti-carcinogenic, and anti-genotoxic properties. The process of these studies begins by subjecting the carrot tissue to a physical stress, such as scratching or UV exposure. Subsequently, 5 grams of carrot are mixed with 20 milliliters of methanol and mechanically homogenized. This mixture is centrifuged at 4000 rpm, and the supernatant is recovered and filtered with a pore size of 2 micrometers. The filtrate is analyzed with the Uhplc to quantify the phenolic compound with the diode array detector at 4 centigrades and 320 nanometers wavelength. Finally, using a reference control with a known concentration of the interest compound, we can verify the presence of the analyte in the sample by comparing the retention times and measure its concentration by calculating the area under the curve of the resulting peak.